Hello, welcome to this discussion on making materials using Lightwave. We're taking a slightly different approach in this video tutorial. Instead of working on a project with specific models, we're going to start simply by looking at all the parameters and values involved in materials, and we're going to talk about how they relate to material reality. In the first section, we're going to cover material basics, and that means we're going to look over the surface editor here and look at all the different parameters in the surface editor, and we're going to try to find a way to relate them to reality so we can understand what each of these things really means when it comes to realistic materials. And this is crucial in order to create materials that stand up properly under different lighting conditions. Now understand that one of the greatest problems CG artists and especially lighting and shading artists face is the problem of creating materials that work correctly under all lighting conditions. It's quite easy to create a material that looks fine under a single lighting condition, but if that material is then put under different lighting conditions and looks wrong, we call that an invalid material. And if a material is invalid, in other words, if it doesn't look right under both, for example, daylight and moonlight, then there's a fundamental error in the creation of that material. We're going to talk about the prime culprit in creating invalid materials, and that's a concept called decoupling. And decoupling occurs when you have various material parameters that belong together that are separated so that you can adjust them separately. And that's usually where we run into trouble if we don't know exactly what we're doing. We're also going to spend a little bit of time talking about the concept of energy conservation. Energy conservation is kind of the opposite of decoupling. It's a concept whereby we create materials by keeping in our heads how much light there is hitting a material and then how much light is reflecting from that material. And the basis of the concept is that there should not be more light reflecting off of something than is arriving at it. That's physically impossible. And we run into a lot of problems by ignoring energy conservation. Now that's not to say that we always have to calculate our energy so that light in matches light out perfectly, but we should keep it in mind as a rule of thumb if we're trying to create valid materials. After we've gone over our material basics and have attempted to gain an understanding of all these parameters and the many more that exist in Lightwave, we're going to have a second section where we're going to actually create materials from photographic reference. So we're going to make some common materials like chrome, gold, brass, glass. We'll probably do like window glass and then perhaps a vase or a wine glass or something. We're going to look at creating a good looking plastic shader. We're going to look at doing human skin, including subsurface scattering. And we're going to look at other materials like wood and stone, and common materials you might find around your house or in your environment. Following our section on creating good looking materials, we're going to take a little bit more advanced look at materials. And in this case, we're going to pop into the node editor and we're going to discover some of the power that exists inside this innocuous little button on our surface editor. It's actually incredibly powerful. But before we begin, I want you to keep this one concept in mind. Creating great materials is a lot easier than you think, provided you have a decent understanding of how real materials work, how real lights work, and what each one of the parameters in your lighting and shading tools is intended to do. Okay, before we get going, talking about the different material parameters we have available to us in Lightwave, we need first to have a discussion about human perception and the act of seeing. Many people perceive seeing as some kind of projection out into the world. So you see a desk in front of you, you're looking at a computer monitor or some other display device right in front of you right now, and you have a sense that the seeing is occurring outside of your body, out in front of you. We need to reverse that and understand what's really happening. What's happening is that light is emitting from light sources like the display device in front of you, and it's coming into your eyes where it's perceived. Or if you look at a floor or chair or table or a wall near you, you can see that light is coming from light sources and hitting those things and bouncing off of them, and that light is now entering your eyes. So you're not actually seeing the display device or the chair or the table or the floor or the wall, all you're seeing is light that has been reflected off of that. That light is entering your eyes, it's hitting your retina, and your retina is reacting and perceiving the light that hits them and is sending signals to your brain, and your brain is interpreting it. So to begin with, we must understand that everything we look at is light. If you're looking at something that is colored blue, you must understand that what you're perceiving is blue light. If you're looking at something that is orange, you must understand that what you're perceiving is orange light. Orange light is entering your eye. If you're outside on a sunny day and the sky is blue, and we all know how bright the blue sky is, we can barely look up at it, it makes us squint. That is a major blue light source. So there's tons of blue light coming out of the sky. And even if you simply see a little dot of red paint on the far wall, or some small dot on a distant wall, if that dot has a color, that's the color of the light that's coming towards you from that dot. There is a common misperception that the things around us are colored, but that light is white, and that's a completely incorrect presumption. In fact, color itself is simply a human construct. It doesn't exist in reality. Color is a way of us being able to differentiate between different wavelengths of light. And when I say different wavelengths, what I mean is that those photons are vibrating very quickly, and some of them vibrate more faster than others. And the faster a photon vibrates, the cooler its perceived color to human beings. And the slower it vibrates, the warmer. Thus the Kelvin color temperature scale. And not just the Kelvin color temperature scale, but indeed the entire visible light spectrum. Very low, slow vibrations in the visible light spectrum give us red light, and the faster the photons vibrate, the closer they get to blue light, which is at the top of the visible light spectrum. Now that's getting a little bit more physical than we really need to get into. What's important is to understand that any time you see a color, what you're seeing is colored light. If you take a moment to look around you, you'll realize that almost all the light reaching your eyes is colored. This is one of the reasons why high dynamic range images work so great in image-based lighting, because all they are is a great big spherical light that's shooting colored light in from all angles, various different colored lights, and it provides a beautiful complexity to the scene. So before we get into our materials, it's important for us to understand what light is, what it's made of, and where it comes from. Of course, our three primary colors of light are red, green, and blue. We know this. We work in RGB color space all the time. Right here on in the color channel of the surface editor, we can see we start with a default color of RGB 200, 200, 200, which is a little bit less than white. It's kind of gray. By mixing these three wavelengths of light, we can achieve other different wavelengths. For example, if we have only red and blue and no green, we get magenta. If we only have red and green and no blue, we get amber. And if we have only green and blue and no red, we get cyan. And those are secondary colors. Secondary colors are created by mixtures of primary colors. And then we can get what's called tertiary colors by mixing all three, or by going in between the colors by having different values between the two primaries. If the values are the same, we get a perfect secondary color. If the values between any two primaries are not the same, then we have a tertiary color. Okay, so with better understanding of human perception and the act of seeing, let's carry on and take a first look at our surface editor and the parameters that we find there. Okay, before we get into the parameters, let's just take a quick overview of the surface editor interface. There's a lot of things here you should know. To begin with, we'll just start right at the top. You can edit by object. In other words, there are two objects in here right now. There's one called material test balls, and there's one called second ball. And let me just show you what those are. Go to my objects and I'll select, there we have the material test balls, is all the balls except this one. This is an actual second object called second ball. And that's reflected in here you can see there's the two objects, and within the objects, these are the material names. The second ball only has one material on it, and the first object has a bunch of materials on it, including the ground, and then there are 8 balls in there, each one with a different material name. 1, 2, 3, 4, 5, 6, 7, 8. So there's 9 materials in total inside this object, and only 1 in this object because there's only the one ball. Now I could have assigned any polygons to any surface name, but I simply chose to make the ground one surface name and each of the other balls its own surface name. You'll notice that one of the balls in this object has the same surface name as the second ball. They're both called 1. Now I could, instead of editing by object, I could edit by scene. Watch what happens when I do this. It gives me a warning. It says, surfaces with the same name will be edited as a single surface. Do you want to proceed? I'm going to say yes. So now, if I change the surface of 1, I'm just going to make it luminous, you can see that the surface on both of these objects, even though they're separate objects, edited together. This could be useful if, for example, you have multiple buildings in your scene. All of them have window glass, and you've just named them all window glass. And window glass basically has one parameter. You know you're going to want them all to look the same, so in the process of your modeling you may just name all of your window glass. So no matter now how many objects you have, you can change all of the material parameters on that object at one time by doing it this way. There's another way to do it, but if you have hundreds of different objects and you just want to change all their glass at the same time together, simply edit by scene. The other way to do it is that you can multi-select both of these. Oops. Control select them. If you shift select, it'll select everything in between. So I controlled select both of the ones, and I'll turn the luminosity down again. So that's another way to do it. And that's easy if you have 2 objects, but imagine if you had 100 objects. You might not want to go through and have to select every single material with the same name. So by planning ahead, when in the process of your modeling, by carefully naming your materials in this way, it gives you an option to be quicker later on when you need to make a bunch of changes to materials of the same name. So it's worthwhile to give your surface names some thought, for sure. Also, if you have a huge long list, maybe you have 100 objects in here with a bunch of different material names, you may want to filter them out. So again, back to the glass window, you may want to filter out everything except glass window so you can see them all together. And you can filter here. You can filter by name or by text or by shader or by preview. I'll give you an example of name. So if I wanted to, we know there's 2 materials here with the name 1. So if I put in the pattern 1, there it gives us just the remaining materials. If I put in the pattern 2, it'll only show us the one material with that pattern name. And once again, if I just delete that, it'll show all the material names again. Now up here is a little arrow, and what this does is this will collapse this window, so you won't have your object and material name list anymore. What you will have is a drop-down list with the objects and their material names here, so you can select them one at a time. And typically you would use this if you're really stuck for some real estate on your monitor. I generally work with it wide open. As a matter of fact, I can't even remember the last time I closed it, but that's me. Your workflow may be different. Next, here we have the option to load, save, and rename materials. So if we had set up a material on this material name number 1, maybe it's luminous, and maybe it is amber, and maybe it's highly specular, and we went to a lot of effort to create this material, and we wanted to add it to a bunch of other materials, maybe even in a different scene. We could save this onto disk. Simply click the Save button, and we type in whatever the name of the material. Maybe we want to call it amber spec. Enter, and it will save it as a .srf file. So if we want to load it, say I wanted to load it onto this material, this surface name here, I could go load, and I could load amber spec, and there it is. Now if I'm just working within this scene and this object, it's actually very easy for me to simply go copy. So right click to copy it and then go to another material and paste it. However, if you're working in different scenes and you don't want to have to load the object into the scene to copy and paste its material, you can transfer materials by using the load and save buttons. And as I said, you can also rename, give the material a new name, so I might want to call it 11 instead of 1. But for now, I'll just rename it back to 1. I also want to revert all of my materials back to the gray that we had before. So I'm going to right click, copy the number 6, and I'm going to select all of these, right click and say paste. And now all of them, multi-selected, are the original gray color. Here we have our swatch. So this shows us what the material, this current material, would look like if it were rendered on a sphere. And there are some options here. First of all, we can choose what to display in this window. And here's the display drop-down. It'll show us all the channels that are available for us to display. Render output is the common one. That's all of the channels put together and what the final render is going to look like. But you could render just the color channel. You notice there's no shading on this now. It's showing us just the flat color. We could look at the luminosity channel. Well, there's nothing there yet because luminous is 0. So if we turn our luminous up, we'll get a little bit of the luminous value in there. And this is a good indicator of what our buffer export will show us if we do a buffer export. Diffuse channel. It's showing that this is 100% diffuse, so the whole sphere is flat 100%. That's RGB 255, 255, 255, or if you're thinking in floating point, the values would be 1.0, 1.0, 1.0. We could look at the specular channel. There's no specularity on here yet, so let's turn some up. So what we're saying is that the whole surface is 72% specular. So all this is doing is giving us the value of specularity across the whole surface, so we expect it to be flat. Reflectivity channel, once again, if we turn the reflectivity up to 32%, we expect to see a gray value of 32% in here. And the various other channels pretty much as well. These simply show us the grayscale amount of the values in these channels. This isn't like render passes. For example, if you look at the specular channel, you wouldn't expect to see the specular highlight in here. All we're saying is the potential value of specular intensity across the whole surface. It's got nothing to do with the position of the light or anything like that, so you don't expect to see specular highlights. And that's a little confusing to some people, but hopefully that's clear now. We'll go back to the render output, which shows all our channels together. We also have options for how this is displayed. It doesn't have to be a sphere. For example, here's our options. We could make it a cube if we wish to. Sometimes you don't want to see what it looks like on a sphere, although that's usually the most useful. We can change the sample size. So for example, if you have image maps that are a certain size and you're working at a galactic scale or something, you might want the sample size to be 1 million meters. That's totally allowed. Still looks the same, but you'll see that your image maps and other things that are in a larger scale will now appear a little bit more correct on your swatch here. The background color is synchronized to the background color of layout by default. Now layout is black when you first open it. If you want to change the backdrop color of layout, of course you go over here to Windows, Backdrop Options, and there's tons of different ways you can put backdrop color in, but here's one way. You can just change your backdrop color to, for example, red, and then this will need to be updated. Now the backdrop color is the same color as in layout. Or it can be a checkerboard. Sometimes you want it to be a checkerboard, especially if you're looking at reflections or refractions. Here, let's make this thing refractive, and I'll take a look at it. Turn off the reflections, turn the transparency way up, and we'll turn on a refractive index of 1.3, and now we can see what refraction is going to look like in this material. So the checkerboard can be quite useful, but usually it's either at black or at layout value. And often the layout is black before you get into your final lighting, or if you're not using image-based lighting or whatever. So I'll just set that back to black. You can have the option to anti-alias the swatch. You can see there's a slight image improvement when I turn that on, but at a very slight performance hit. You have the option to use the scene lights or not. And your refresh can be real-time, automatic, or manual. And by manual, it'll be when you tell it to. Usually, you just leave it at automatic, and it updates as soon as you have finished moving something. And I'll show you the big difference between real-time and automatic. Automatic's better because it waits until you have stopped changing a value. If you have real-time on, it won't wait. It'll do it as you turn it up and down. And that can be useful, but in larger scenes, it can bog down. So normally, we just leave that at automatic, and it waits until we've lifted our mouse before it implements the change in the color swatch. So that's it for the display and options. Oh, also to the right of the swatch, you can see there's information about the currently selected material. So we can see that the currently selected material is called ground, and if we look in here, we can see that the ground is just one polygon. So it's telling us that the ground is one polygon, that there's no textures and no shaders applied. If we pick one of the balls, one of the materials on one of the balls, we can see that it's 288 polygons, and that's how many polygons your default ball has in Lightwave. And it's one surface selected. We could select multiple surfaces, and it'll tell us how many surfaces there are. It's multi-selection, how many polygons are in both of those surfaces. And it's saying nodes 2, and it's saying nodes 2 because every material by default has one single node. And if we quickly look in the edit nodes, we'll see that it's the root node here, the main surface root node. So every material has at least one node to begin with. And now we get down into the meat of the matter. Here we have our basic tab, and our basic tab contains the most basic channels that are used in creating a simple material. In addition to that, so we have our color, luminosity, diffuse, specularity, glossiness, reflection, transparency, refraction index, translucency, bump. Those are the basic channels, and we'll go over in detail what every single one of these means. In addition, we can turn on shading smoothing. This isn't the same kind of smoothing that you get in other softwares where it actually subdivides the geometry. This smoothing does not subdivide the geometry. It's just a shading trick so that the edges of polygons don't appear so sharp. And if I switch this into shaded solid mode, and then I select the material for the second ball, which is this one right here, and I turn on smoothing, watch what happens when I turn smoothing on. It looks like it's smooth. Now if you look around the edges, you can still see all the polygonal facets, but it's not shading as though those polygon edges are faceted. This is just a trick to make an object look smoother across faceted polygons. And it actually works quite well in many cases, and it often allows you to get away with a lot less subdivision. Even if I took this object and subdi'd it, and I'm actually just going to do that right now. Here, let me turn off smoothing. I'm going to pop into Modeler. I'm going to subdivide that object with the Tab key and save it. Go back into Layout. And even subdivided, you can still see that it's faceted. And all we need to do is clean up that shading, so we just turn on smoothing. And now it looks really quite nice and round, and it's also subdivided well, so you can't even really notice the faceting around the silhouette either. There's something called a smoothing threshold that's directly related to that, and it's by default 89.53 degrees. What that means is that if the angle between the two polygons is less than 89.53 degrees, then smoothing should be applied. Watch what happens as I turn this material, or this smooth threshold, way up. As I get close to 360 degrees, I'll just slide right up there. So we're getting close. Okay, so if we're at 350, you see no difference. If we go up to 353, you can start to see faceting on some of these, but it's smoother in other areas. And as we go all the way up, closer to 360, you can see that the faceting is outside of the threshold and is no longer smoothed. So you can actually decide what angles to smooth and which are outside of the smoothing threshold by setting this value. If you have an object that has a vertex normal map assigned, here's where you add it. There's a funny little control here called exclude from VStack, and VStack means volume stack. The deal here is this. In the old days, when we wanted to make, for example, a crystal ball, we'd turn our transparency way up to like 98%, and we'd give it a nice glassy refraction index of about 1.3 or 1.4, or maybe a little higher if you're using crystal. And then we go to our render globals, and we would turn on our ray trace refraction, which is on by default now. And then we'd hit our render button. Now let me just go into the VPR instead, so you can see that's refracting. Now in the old days, the refraction didn't work properly unless you had another set of normals also facing inward. So by default, all these polygon normals are facing outward. And just making the polygon double-sided would make it change, and you can do that just by clicking the double-sided button, but it didn't work quite physically correctly. So what we would have to do is we would have to copy the polygons, flip them inside, and paste them into the object again with the same material and the same refractive index. Well, what they've done is they've added this thing called a volume stack, and it means that you don't have to do that anymore. So this will render correctly without having to have an extra set of inside polygons. Now there are some cases in which you might wish to turn that off, so that that's not happening. And if you want to turn that off, that's how you do it. Exclude from VStack. And as I just said, double-sided simply makes a polygon double-sided. So let's turn this down, and I'll show you what I mean. And I'm actually going to turn off the smoothing on this object, and I'm going to go back into the modeler, and I'm going to unsubdivide this object, and I'm going to flip its normals with F. Now that I've flipped the normals over, you can see the ball appears to be inside out. I'll save that and pop back over into layout, and in layout here, here's our ball. The normals are inside out, and it's all dark, and you may wonder why. If the normals are inside out, it just doesn't look inside out. The reason is because although it's inside out, it's still casting shadows on itself, so it's completely dark inside. So let's see if we can get some light inside there. We'll open up the object properties for this object, and down here we can see self shadow, cast shadow, and receive shadow. So we'll turn off self shadowing, and now we can see the light on the inside of itself, and we can see clearly that the object is inverted, normals inverted, and we can switch that around by making it double-sided. Now that double-sided does not invert the normals. The normals are still facing inside, but it's also calculating rendered polygons on the outside as well. I normally try to keep my normals in the correct direction, and I'm pretty anal about that. And the only usual time that I use double-sided is if, for example, I may have a pane of glass that I happen to be seeing from both sides. And no, your glass does not have to actually be thick to be correct. But if I'm in a hurry and I find that a bunch of polygons are messed up in a model and I just really need to get it out, I may just select all the materials and make them double-sided. Now this may mean a little bit of a render hit for me, but if I'm under the gun and it's that serious, I probably don't care. So normally double-sided is a quick fix for me, and I actually very seldom use it in final materials. And you can also put a comment in for your material. There's an advanced tab here. You can set the opacity of the material in the alpha channel, and we'll go over that. You can set special buffers here. You can create a glow. If you have glow enabled, you can do a kind of a post glow on a material, although that's not really recommended for production. You can render outlines of the items. You can there's all kinds of stuff here that we can do. Color highlights is especially useful in bringing the color, the material color, back into an object that's highly reflective. And we'll talk about what's broken about that. There's a compatibility button down here if you happen to be using older materials, normally just at default. And if you're starting out new, or if any of your materials are built in Lightwave 9 or 10, you don't even have to worry about that button. Back here is an environment tab, and this is a way of putting an image in the backdrop that will render with your materials either through reflections or refractions without having to be an object in your scene. That's kind of a quick way of putting a reflection image or a refraction image in there. Something you want to refract through glass, or something you might want to reflect in the chrome or whatever. And we'll be looking at using this as well. There is reflection and refraction blurring. So we can blur refraction as though to make the material look as though it were, for example, a sandblasted glass or something. However, there are far better and faster solutions. This is a pretty old algorithm, and it's pretty render intensive. And if you're going to the trouble of blurring your reflections or refractions, it's much better to do it in nodes. It'll render a ton faster. But we'll try practical examples of these as well anyways. And then the last tab here is the shader tab. Now, what shaders mean in the context of Lightwave is not the same as in the context of other softwares, where a shader is something that you apply to an object to make it render a certain way. In Lightwave, a shader is a special piece of coding that allows you to add some kind of an effect to your surface. You know, you can make checker maps, you can do your typical color cube, you can do a Fresnel effect. Gmill is a kind of an occlusion shader. Snow kind of puts snow on the top of things, so it looks at the angle relative to the horizon. There's a whole bunch of different shaders here that you can use. And that pretty much covers it for the interface for the surface editor. So next, let's start taking a close look at the channels in the basic tab and see if we can wrap our heads around what engineers meant when they added all of these different parameters to a surface. It may surprise you to know that real materials have one and only one parameter, and that all of these separate channels that have been defined by these software engineers are controlled by that one single parameter. So in fact, each of these different channels are different ways of expressing that one single parameter in reality, and have been split apart so that you have individual control over them. So all of these perceived values have been decoupled and put in front of you, and this is where so many people run into trouble in creating materials, by not understanding that if you change one thing, you should really be changing 3 other things if you want your material to behave photorealistically or close to photorealistically. If you're creating materials for non-photorealistic applications, then you know all bets are off. You can do, of course, whatever you want, but it's still going to help you if you deeply understand the nature of real materials and real light in trying to create materials that are representative of those realities. So in our next section, we'll start looking at these channels and what they mean. Alright, to begin with, let's take a look at the first channel, the color channel. And this seems fairly self-explanatory. You set a certain color in here, and that's the color that your material becomes. So we're going to take this ball here, and we're just going to turn up the red and turn down everything else. We're going to make it red. So we look at this and we say, this ball is now red. And this is a way of perceiving what's happening with light here, but in order to create really valid materials, we need to understand the physical process that's happening with light and material and what CG is doing to mimic reality. So in order to do that, first we need to understand reality. So let's look at some photographs. Here's a picture of some faded blue jeans. There's a lot of blue in there. This doesn't mean that the material is blue and that white light is shining on it, so we're seeing blue under white light. What it means is that white light, and you can see the light is white because it looks, where it's close to white, it's a little bit yellow, is shining on this white table down here. So this color of light is shining onto the blue jeans, and the blue jeans are absorbing some of the light, and they're reflecting some other light. Now, let's just say the light shining on these blue jeans is theoretically perfectly white, so therefore it has equal values of red, green, and blue light, equal amounts of those photons in that light beam. If the genes are blue, it means that this material is absorbing most of the red and most of the green, but it's not absorbing the blue light. The blue light is reflecting off, and that's why the genes appear blue, because they're absorbing most of the red and green light, and they're reflecting most of the blue light. That's why something looks blue. Something looks the color that it is because it's reflecting most of the light in that area of the visible light spectrum. Let's look at another picture here. This is a piece of almost white carpet. What this means is that this material is configured such that it reflects most of the red light and most of the green light and most of the blue light. If we look at this carpet here, there's reds, there's greens, there's kind of grayish blues, and in the red areas it means that those fibers of this carpet are absorbing most of the green and some of the blue. You can see it's a little bit pinky, so it means that there's blue and red both in there. If you look at the greener areas, it means that these areas are absorbing most of the red and most of the blue and reflecting some of the green light. Let's look at another image. This is a very colorful image. There's yellows, there's blues, there's grays, there's greens, there's reds all in here. And you can tell what light is being absorbed and what light is being reflected simply by looking at it. If you look at this one here, there's a lot of amber light in here. So amber light is being reflected. What's amber light made of? Amber light is made of a mixture of red and green light. So most of the red and green is being reflected and most of the blue is being absorbed by this rock. If we look at this image, there's a picture of me and I'm wearing an orange t-shirt. So we can see that right here what's happening is orange light is being reflected, and that's going to be mostly red and some green and very little blue. So that shirt is absorbing most, if not all, of the blue light, and then down here again you can see blue jeans and they're very blue. So that means it is reflecting most of the blue light and absorbing most of the red and green light. Now I don't want to go on and on about this, but I do want a clear understanding of when we say color here, what we mean is what is being reflected and what is being absorbed. So when we turn this red value up to 255, which is the maximum value, what we're saying is that of the light that is shining onto this material here, all of the red light is being reflected, and all of any green light that's shining on that material is being absorbed, and any blue light that is shining on that material is being absorbed. That's not the way it's working physically. What we're actually doing when we turn this up and down is we're telling the computer to turn only the red portion of the pixel on, and we're telling it to leave the green portion off and to leave the blue portion off. So that's the computer engineering behind what we're seeing. But we have to understand that this computer engineering is designed to mimic a real physical behavior that's created by real physical materials and real physical light. And we can get much closer to making our materials look realistic if we begin with a deep understanding of how materials and light interact, because our tools are designed to mimic that behavior. It's just that most of us are never taught this stuff, so we don't know, so we go through all kinds of presumptions and end up with terrible looking materials and don't really understand why. That's what this video is about, is to try to help you understand how reality works and how your tools are supposed to relate to reality. So let's just reiterate. Color is split into three distinct colors, the primary colors of light: red, green, and blue. Those red, green, and blue colors are defined by the speed of the translational motion of photons. That's not as important as understanding that there are three different colors of light that humans perceive, and that those colors are defined by the color wavelengths. And that all the colors that we see, any colors that we human beings can perceive, are simply mixtures of these three colors of light. And that when we say something is a color, what we're saying is that's the color of light that that material is reflecting. So color is all about light reflection, as are most of these parameters, as a matter of fact. So the color can be defined by dragging these three sliders here, or you can click on a color swatch here. When you click on a color swatch, you're going to get this Windows color picker interface, which is actually a really terrible interface. It works in hue, saturation, and value, but it's not really a very awesome color picker. So I recommend that if you're going to be picking a lot of colors, you should probably switch to the Lightwave color picker, and I'll show you how to do that. Type O for options, and right here in the general tab of preferences, under color picker, default is the Windows one. You want to pick the Lightwave color picker. And when you pick the Lightwave color picker, now when you click on a swatch, you're going to get this interface. This is actually 5 different color pickers, which is pretty awesome. Quick color, which allows you to just dial in hue, saturation, and value, or RGB values quickly, so you can quickly create a color numerically. Once you've created a color, you can store it down here by clicking the Store button. And then if you decide you want to use that color on something, you simply select the square, click Use, and that will go onto the currently selected surface. So that's called Quick Color. There's this one, HSV RGB. So this describes colors in more of an artistic palette. And I want to take a moment to talk about HSV versus RGB here. Now, RGB, red, green, and blue pixels, is what most CG artists think of and work in all the time. The problem with RGB is that it's a mathematical way of expressing colors. As artists and as human beings, we don't experience colors in terms of RGB. We don't look at a wall and say, wow, I wonder what the RGB value is of that wall. We wonder about its hue. We wonder about how saturated the color is, and we wonder about its value. And if you're not familiar with those terms, hue means the color, and if you look on this color picker, hue is right across the top here. It's pure color. That's what hue is. And then saturation means how faded or not that color is. So a color that is highly saturated might be, for example, this blue. This is close to primary blue. Here, let me make it actually all the way to primary blue. So there's primary blue. So that's a 100% saturated pure hue. If I were to reduce its saturation, just drop down lower here, watch what happens in the color swatch. It becomes faded. It fades more and more. And once we're at 0 saturation, we have pure white. Less saturated is kind of more pastel, kind of more faded. And when we think about experiencing colors, you may remember I was talking about the faded blue jeans. We don't wonder about what the RGB value was when we bought the blue jeans, and then what the RGB value is after we've worn the blue jeans for 10 years. We look at those blue jeans and we say, wow, those are faded. The hue has faded. It has become less saturated. So we actually think in terms of hue and saturation. And what value is the hue between its pure value, its pure color, and black. So it's kind of the opposite of saturation. Saturation is hue to white, and value is hue to black. So once again, when we see a pair of jeans that is faded and old and has low saturation, and then that jean gets really dirty because it's been out in the rain and through the mud and everything, we don't wonder what the RGB value was before it got wet and dirty, and we don't wonder about what the RGB value is after it got wet and dirty. All we know is that it's darker. It's the same hue, but it's just gotten darker. And in artistic terms, we call this value. So a low value is close to black, and a high value is close to the original hue. So you see that we understand and perceive and experience color in terms of hue, saturation, and value, and not in terms of RGB. So it's interesting that as CG artists, so many of us always have worked in RGB and don't really see a reason to switch to HSV. However, if you are in the process of creating realistic materials, and you want to create a, say for example, you need to create a house for a shot, and then you want to create that same house 25 years later, or you want to make a house that looks old and beaten up. Instead of picking an RGB value, you pick the color of the paint that the house might have, and then you simply fade it. Instead of trying to fiddle around with RGB values to find a faded version of that color, just turn down the saturation. And I'm going to show you a really fast way to do that. Over here in your color picker, instead of just sliding these things around, what you can do is anywhere you have a 3-vector color input, you can right click and switch it into HSV. Now you can pick your hue. Of course, you're not going to see any hue because the saturation is 0. So let's turn our saturation up and let's move along with our hue. Hue, saturation, and value, if you've been working in RGB space for a long time, hue, saturation, and value is going to start by feeling kind of alien to you. But if you can really knuckle down and put the time into learning to really understand HSV, I think you'll find you seldom go back to RGB color except for specific technical reasons. For artists who are looking to create materials that are realistic or that have certain senses, certain feelings, I think you'll find that if you spend time working in HSV instead of RGB mode, that you'll get where you need to get a lot more quickly, and it will provide you with a deeper understanding of the nature of color. So let's just look back at the color picker for a minute. So that's HSV and RGB, and right down at the bottom, once again, just like the quick color, these interface items are in the HSV RGB down at the bottom, both the RGB values and the HSV. And if you change any of the RGB values, you'll notice that the HSV values also change. Watch. So they're interconnected. Once again, once you find a color that you like, you can store it in here. And then later, if you want to use it on something, you simply click on the square of the color you want and click Use, and it will go into the currently selected material. We also have something called Tint and Shade here. I actually have never really understood the purpose of this, although I understand that painters use this color picker a fair bit. However, I personally have never found it useful. That doesn't mean it isn't useful. That just means that I have a different workflow, and you may find it incredibly valuable. What we're looking at complementary tints here. So the tints at the top are complementary to the hues at the bottom. So that could be what that's about. If you want to look at just pure hues and nothing else, we look at the wavelength color picker. So for example, if you're working in physics, if you say for example you're creating a rainbow and you need specific colors at specific wavelengths, and wavelengths are measured in nanometers, and you can actually type in the physical wavelength and get the associated color. I actually have never used this, but on the other hand, I do mostly film and television and commercial video effects, and not physical models. So I imagine this could be incredibly useful in the cases where you're doing physical models and need really correct data. And then this is my favorite color picker of the lot. It's the Kelvin color temperature scale. I love this color picker because I'm a lighting supervisor and a visual effects supervisor, and I spend most of my time looking at the quality of light in CG renders and in compositing. And in the case of my work, where I mainly do visual effects, what's important about the light is that it begins in close to the correct color world. And the Kelvin color temperature scale correctly expresses the color of real incandescent illumination. So by incandescent, I mean it could be a match or a candle. It could be a hot element on a stove. It could be a welding torch or a light bulb. It could be a mercury vapor lamp. It could be anything that's incandescent, and it goes all the way up to skylight color. Because skylight color is simply sunlight that has had most of the red and green light, the amber light, stripped out of it, and what remains is this skylight color. So the Kelvin color temperature scale covers so many of the colors of natural light. And in fact, you can dial in the Kelvin temperature right here. I happen to know off the top of my head that a typical household light bulb is anywhere between 2800 and 3200 Kelvin. So let's say an average of 3000. So I know that if I create a light bulb and give it this color to emit, that'll be about right. Now, speaking of this color, you may look at this color and go, no way, light bulbs are way whiter than that. You need to understand that that is a flawed human perception, that the light is around this color roughly, and that your brain color corrects things to make the light seem to be white. Additionally, a light source right at its filament is so incredibly bright that it actually overloads your retina, so it's too bright for you to even perceive that color if you're looking directly at the light source. It's called clipping, where the actual amount of light overloads the ability of your retina to perceive it. In photography, this kind of clipping is known as overexposure. So a light may have a color, however in the photograph it looks just like a white circle, a circle of pure white, because the camera can't perceive the brightness. And you'll know this if you've ever taken a photograph where the sun was right in the frame. You can't see a round ball with flames on it. All you see is a huge white flare and this big, totally overexposed white mess in that area of the frame. So that's what clipping is about. So part of creating materials is understanding that we have flawed human perceptions, and this is just one of them. So if I was making direct sunlight, I might go in the 5500 to 6000 Kelvin range. That's roughly sunlight. You can see how close it is to white. It's a little bit amber. The reason why sunlight here on Earth is amber is because the blue light is stripped out of it and is dispersed around in the sky, and that's why the sky is blue. If I wanted to do skylight color, I might do something in the 10 to 20,000 Kelvin range, depending. The sun gets deeper blue as you get closer to the zenith. So this is a great place to get natural light colors from. And if you're doing visual effects, or if you're doing outdoor lighting, or if you're doing anything incandescent, just do a Google search for Kelvin color temperature and you'll find lists of the Kelvin color temperatures for various light sources, and you can type in the value here and pull it directly in. And I guarantee you that when you first start putting them in the scene, they will seem wrong. That's not because they're wrong. It's because you're working in a CG environment with all kinds of decoupled values. So all kinds of values that are not working in concert with each other. And part of the purpose of this video is to try to create an understanding between the parameters of reality and the parameters of our CG scenes. So that kind of covers it for the color. And just before we move on, I just want to cover these two buttons. E envelope means animation graph. So if I click on the envelope for the color channel, what I have here, I'll just drag this out here so we can see, is I have three channels: color R, color G, and color B. And what I know, it tells me actually the name of the object, second ball, and it's telling me it's a surface channel, and it's telling me the name of the surface, 1, and the channel, color .R, which is color red. I can actually animate these over time. So I could, for example, add a few keys to my red channel. And I'll just make this one 0, a value of 0. And you can see that over time you can see what the color is going to be. I'm going to go to my blue channel. And I'm also going to animate it. So you can see that if you were creating lights and you wanted them to change colors like disco lighting or something, it'd be very easy to do just by opening up the envelope for the color channel. And this is for a surface. You can do it on surfaces as well as lights. Anything that has a color channel and an envelope beside it, you can do it. And then I'm just going to try this. I have the VPR rendering, so this real-time render is going on. I'm going to slide this along and see if this works. So there you go. So you can actually see the color changing as I move the timeline along. So that's a pretty neat feature. If you accidentally click on the envelope, it's very easy to remove. Simply shift click it, and the envelope is gone. Over here we have a T, that's for a texture editor. So this color on this material can either be just a straight color, or it can be an animated color, or it can be a texture. And I'm going to get an editor when I open this up, and here it is, the texture editor. So it's saying this color can be one of three layer types. It can be an image map, or it can be a procedural texture, or it can be a gradient, and we'll look at all three of those later. If it's an image map, we can project it in a bunch of ways. We can do planar projection, cylindrical projection, spherical projection, cubic front. The most common these days is UV projection, so typically your geometry will have a UV map on it, and you'll have a color image that is painted to match the UV map, and then you'll apply it in this way, and we'll look at that later. If you're using a cylindrical projection, for example, you can pick which axis it unwraps on, or it's true of a spherical as well, you can pick the axis. If it's a planar projection, which means it's directly orthogonal along the X, Y, or Z plane, and once again you can pick the texture axis. And cubic is actually useful in many ways because it allows you to put a texture on anything that's cubic shaped. Like for example, if you had a picture of wood and you wanted to put it along a whole bunch of boards on a veranda, it'd be really easy to use cubic and you wouldn't have to go through the trouble of creating a UV map. And over here you can add layers. So you can have one layer for your image map. You could add another layer and mix a procedural turbulence with it, for example. You could add a gradient to that. And you can mix these layers using the blending mode, and by default they're all normal blending mode, which means the top layer is going to be 100% and the other ones underneath aren't going to be seen. You could there's a whole bunch of, you'll recognize this if you use Photoshop a lot. Typically you might use a multiply node, Photoshop multiply. There's all kinds of different layer blending modes here. And if you're using a gradient, you can set it up here, and we'll look at how to set up a gradient later. So I'll just close this out, and for now I'm just going to remove that texture. Once again, shift click to remove it. And that covers everything in the color channel. I know you probably came into this thing thinking that the color channel would be very simple. Simply set a color and there it is. But as you can see now, there's a lot more to the color of an object than simply setting its RGB value. Much more. And hopefully a deeper understanding of what's happening when we say color will enable you to create a lot more realistic materials when we get to our demonstration section. Okay, next let's talk about luminosity, the next channel. Now luminosity is a fairly self-explanatory word. It means whether or not the material is luminous. And luminous simply means, is it emitting light? So if we turn up luminosity, we can see that it kind of looks like a bright light bulb, except that it isn't actually emitting any light. And we'll look at it actually emitting light in a moment, but let's compare this to what this parameter is called in other softwares. Most other softwares refer to this value as something called constant. In other words, if the luminosity value is up to 100%, that the whole material should have a constant value on it. So we're mixing actually a light and the luminosity. So let me just turn the light off here for a second. I'm going to open the light properties, turn off the light. So now you can see why it's called constant. It's because the luminous value makes every pixel on the surface of this ball, on the surface of this material, one constant value. If there's nothing else, if there are no other factors like other lights or specular highlights or whatever. So this acts like it being a light bulb. Now we can make this actually emit light into scene simply by turning on global illumination, radiosity for example, and I'll show you how to do that quickly. We go to our render globals, go to our global illumination tab, and as soon as we enable Monte Carlo radiosity, you can see that it's actually emitting light into the scene. So this actually feels like a light bulb, and it'll feel a little bit more like a light bulb if we would give it a light bulbish color, such as 3000 Kelvin. That's more of a light bulbish color. It's not the right intensity by any means. I mean, well, I shouldn't get into that, but for this to be a realistic light intensity, the luminous value should be something like 10,000. And you see why the light seems to be white now? It's because the amount of luminous value on the light is clipped past the display value, just like a real light bulb would be. But for now, let's just stick to around 100%, and we can see that it's luminous. Now, this is a good value for luminosity. If you're actually making something that's supposed to be emitting light into the scene, you use luminosity and make it luminous. However, a lot of people use it in a different way, and let me show you what I mean. I'm going to turn this back down. I'm going to turn our light back on. You'll notice that you can actually see these balls even though the light is turned off, and the reason for that is, if we open our light properties, we can see that the ambient intensity is at 5% by default. So that's ambient intensity is actually another way of doing constant. If I turn this up to 100%, then everything is constant. Everything's perfectly flat. So that's a way to do constant globally. Or you can do constant in the scene by material by using luminosity and turning off global illumination. Now, as I was saying, people have a way of using a constant that isn't great. So let me turn my light back on. So we have a light, and they might say, well, I want to fill in the shadow side here. So I'll turn up the constant a little bit. And that kind of acts a little bit like a fill light. This is a very common error, and I say error because this is automatically creating an invalid material. What I mean is, and I said this before, an invalid material is a material that looks fine under one lighting condition but not under another lighting condition. So what if we had a scene here and we put constant in all of these balls? Let's do that. Let's put a little bit of constant, a little bit of luminosity in all of those balls, 1 through 8. I'm going to turn up the luminosity a little bit to give it a little bit of fill light on the fill side, just a little, just so it doesn't feel so pitch black. That's not bad. Okay, so with our constant using luminosity as a fill light in the side, what happens if we turn the lights off? Well, let's look. Let's turn this light off. This is what happens. Our lights glow. They continue to provide a value when they're supposed to be in the dark. This is a classic example of an invalid material. And the lights don't have to be out. You could be going from a daylight to a moonlight, or from direct sunlight into shadow. And what will happen is these sides that are supposed to be illuminated by a fill light source won't change when they move from one lighting condition into another. They'll stay exactly what they're supposed to be, which is constant. So when you turn up constant, you have to understand that you're forcing it to have a minimum value no matter what happens with the lighting around it. So using constant as a fill light is actually a really bad idea. There's way better ways to do fill lights, for example, by using fill lights. And fill lights can take many forms. They can be actual bounce lights that you can place in there, or ideally they will be global illumination. So let's look at a really good way to do that. If we turn on render globals, we enable radiosity. To see all that light, the key light is hitting and is bouncing up onto the bottom of these things. And that's really beautiful, natural fill light. It's directional, and it will change as the object animates through the scene or as the light animates through the scene. So this is a great way to do bounce lighting, to do fill lighting. Or you can add another light source. The bad way to do it is by using a texture to clamp that fill side at a minimum value. So with luminosity, you do not actually have separate control over the luminosity of the red, green, and blue channels. Luminosity is one value over your color. So we're multiplying the value of luminosity by the color. And so that enables you, if you want to change your luminous color, you simply turn up luminous and then change your color, which is just fine. All of these channels, I think, Yeah, all of these channels could technically be split into RGB, but color is the only one that is RGB, and there's a great reason why at least reflection should be split into RGB, but it isn't, and I'll get to that when I get down to reflection. So again, with luminosity, you have a slider here instead of a swatch because you can only go up and down from 0 to 100%. Now remember this, all of these little spinners, all of these values, they stop at 100% if you're using the little spinner. You can go above 100%, you simply need to type it in. And there's nothing wrong with putting 1,000,000% in there. There's nothing wrong with that. Well, except in the case of this render, you can see it's making some pretty wacky radiosity evaluation, so it's pretty out of control in this context. But there are many cases in which a light may be at a value of 100,000 or 1,000,000%, and it's just fine, especially if it has physically correct fall off, which is in Lightwave we call inverse square fall off. The luminosity can also be animated with the E button. Once again, you get your animation graph and you can animate that so that if I now run my time slider, let me just close these up. If I run my time slider, so we get that value animated, which could be great for, I mean, you could just watch that play and imagine it's kind of like a candle or a firelight. And I'll shift click to remove that. You can also apply a texture to it. So you can put an image map, but just like the color texture, I'm going to put a procedural texture on and watch what happens. Let's see, I want to make this, I'm going to make it 0.1 meters in scale. And I'm going to smooth, actually I want to smooth this so we can see it better. And I wonder if I can improve the contrast here. There we go. You can see that I've applied a procedural texture to the luminous value, and that breaks it up. You know, there's tons of different procedural textures that you can use. Veins, or that's kind of an interesting, creepy alien one. There's tons of them in here, but you can apply those using the texture editor just the same as you could in the color channel. So you can use a procedural texture or an image or a gradient, and that about covers it for the luminous channel. So luminosity can be used for constant, but it needs to be used with caution and with understanding about what's going to happen when you change lighting conditions. Typically, I use luminosity for luminous materials like lampshades where the lamp is on, or light bulbs, or computer monitors, or something like that. So that covers luminosity. Okay, next let's talk about the diffuse channel. The diffuse channel is essentially the same as the color channel. It controls the same kind of values, but in a different way. Whereas, remember we talked about the color channel and how the red, green, and blue channels of color actually mean how much red light is reflecting off the material and how much green light is reflecting and how much blue light is reflecting. Well, the diffuse value means how much light is reflecting as well, but it combines all three of those. So it says how much red, green, and blue light is reflecting off the material. Now let me demonstrate what I mean by that. If we set all three of our color values to 255, the material color is white. If we take our diffuse down to 50%, then the color is 50% gray. Or we can turn our diffuse back up to 100% and we can put our three RGB values down to 50% of 255. 50% of 255 is about 127. So let's just say, actually we can do that by switching to value. We can say about 127, somewhere around there. That's pretty close. So the value, final value is the same whether all three colors are turned down or diffuse is turned down, and that's because it's two different approaches to doing the same thing. You can either turn down the amount of color that reflects individually by going through the RGB channels, or you can do it all collectively at once. And obviously it's a lot easier to do it with the diffuse channel. And the idea here is that what you're doing is, instead of changing the color, is you're bringing the value down. And I refer you back to our discussion about hue, saturation, and value. Well, diffuse is just another way of expressing value, and it means how much light is reflecting. If the answer is 100%, it means all of the light that is hitting this material is reflecting. If the answer is 50%, then half of the light that is hitting this material is reflecting. So diffuse is just another way of saying reflected light. Now, we're not talking about reflection in terms of what you see in a mirror. Reflected light is simply light that bounces off of a substance. And in most cases, the material isn't smooth enough to reflect an image. The image gets diffused. It gets scrambled up. All the rays of photons that hit, they don't maintain their structure when they bounce off. They kind of scramble into a whole bunch of different directions, and therefore the image becomes so blurred that you can't even see it anymore. For example, if you look at a white piece of paper, that white piece of paper, if it's theoretically perfectly white, is reflecting 100% of the light. If you instead look at a mirror, a piece of mirror, that mirror is theoretically reflecting 100% of the light. And the difference between those two materials isn't how much light they're reflecting, it's how they're reflecting it. The surface of the mirror is incredibly smooth, so the light, when it reflects, maintains its structure. That's why you can see the image. Whereas the light reflecting off a piece of paper becomes scattered, and therefore the light does not maintain its structure, and the image information becomes lost. It becomes blurred out. It's out of focus. So that's what we mean when we're talking about diffused reflection. We're talking about reflected light that is diffused so that the image is no longer visible. Either way, we want to look at both the color channel and the diffuse channel as referring to reflected light. Color channel simply reflects light according to whether it's red, green, and blue, so the primary colors are split up. And with diffuse, we're referring to reflected light, but we're not splitting up the red, green, and blue primary colors. We're changing the amounts equally, and we can use this diffuse as a value. And as a matter of fact, if we right-click on color and do HSV, a value of half will be the same. And I'll just change this to 127. I'll find another ball that's near it, and we'll set its diffuse value to, there's one. So we'll set that one's diffuse value, we'll set its color value up to 100%, so it's RGB 255, and we'll set its diffuse value to 50%. And you'll see, I'll turn smoothing on here, you'll see that these two color values are identical. Do you see that? And I'll find another one here. Let's see, let's try this one here. Yeah, okay. And this one instead, I'm going to change the RGB values to 127. This will take a little bit longer. Okay, and turn it smoothing on. And you can see that these three balls are absolutely identical in their gray color. So one of them has the value set to half, 50%. 127 is roughly 50% of 255. It's actually 127 and a half, but we don't have that increment in here. One of the balls has a value of 100% and a diffuse of 100%, and one of them has RGB values of half and diffuse of 100%, and all three of them are identical. So these are just different ways of expressing what light is being reflected off of this material. These values have been decoupled so that we can change the color and then after that make it darker or brighter. We actually never have to use the diffuse channel. If we're just doing an overall value change to the material, we can just right click here and use value. Where diffuse comes in handy is where you want to apply a texture in the diffuse channel. So for example, if you had a machine and you wanted it to be darker in the crevices where it's kind of dirty, then you would paint low diffuse value in all those little cracks and crevices, and then apply it with an image map, and that would bring the value down just in those areas. So it's very useful to have diffuse separate from color, and also to apply a separate texture map for diffuse, but it's not always necessary. So that covers what diffuse is. Once again, the slider goes 0 to 100, but you can manually set it up to 5,000 if you want. Now this is interesting. I've set the diffuse value up to 5,000%. What that means is that this is reflecting 50 times as much light as is hitting it. This is a classic case of decoupled values. One of the things we're going to talk about is conservation of energy. And what that means is that a material can never reflect more light than is shining on it. If you have 10,000 lumens shining onto a material, it cannot reflect 20,000 lumens. So let's say this was 1,000 lumens hitting this ball. We've set the diffuse value to 5,000%. So what we're saying is that it is reflecting, if it was 1,000 lumens in, we're saying that it's reflecting 50,000 lumens, and that's obviously physically impossible. It's useful to know this to create certain effects and to hack and trick your way out of difficulty, but it's very important to, when you set diffuse above 100%, to understand that you're choosing to reflect more light off of this material than is hitting it. Of note, you can't do this with the color channel. Since the color channel is RGB, you cannot go above 255. Now, it's my opinion that the 255 RGB values in the color channel, in all of the color channels throughout Lightwave, should be switched to floating point values. And floating point values mean that in place of a 255 you have 1.0, which means 100%. And the beauty of floating point is if you have 1.0, you can go to 2.0. There's no upper limit, and nor should there be an upper limit, because real light exists far beyond RGB values. Real light is much, much brighter than the RGB values that you can see on your computer monitor. But that's a discussion for another day. In the meantime, let's talk about conservation of energy. Color conserves because it can never go above 100%, at least not with these. You could do it with a texture map. For example, if you used a high dynamic range texture map, you could put your color at values above 100%. But the diffuse value can go above 100%. It can go 1,000,000% if you want. Check that out. So this is ignoring conservation of energy if you go above 100% with your diffuse value. Sometimes you want to do that. All that's important is that you're making the decision deliberately. You understand what the consequences are, and basically you also understand what to expect if you decide to put your diffuse reflection value above 100%. This can also be animated like the other channels, and it can also have a texture map applied, so you can put a procedural texture or a gradient or an image map into the diffuse channel. And that's the envelope in the texture is true of all these channels here on the basic tab. Okay, next we have the specularity channel. And this is where we get into a little bit of weirdness in terminology. We have, you'll notice there's a separator here, and we have specularity, glossiness, and reflection. So it looks like we're kind of separated into areas where color, luminosity, and diffuse are about the outward color of our material, and then we have specularity, glossiness, and reflection. This seems to have to do with reflections, and then we have transparency, refraction, and translucency, which seem to have to do with light transmission through the material. And then of course at the bottom we have a bump map, which is a fake displacement. I think we've fairly well established that color and diffuse are light reflection. Luminosity is light emission. Specularity is also light reflection. Specularity and reflection are two parts of simply the reflection of light. And there's a good reason why they're separated. What specularity is in CG terminology is the reflection of a light source on a material. So if we turn up our specularity, you can see here, let me turn on smoothing on this ball. You can see that you can start to see the light reflected up here in the material. And the specularity can also go above 100%, but you have to type it in. So as you turn it up, it gets brighter. So the specularity here in CG terminology means the brightness of the specular highlight. Now it looks like it's making the specular highlight larger and smaller, but it actually isn't. What's happening is, at a very low value, somewhere around here, around 22, 23%, we're starting to see a disk of white. And what that means is the values within that disk of white are above pure white. They're above the highest value that our monitor can display. So we can't see those values. There is a fall off to brighter happening in there, but we can only see a brightness of white and no brighter than that. As I turn this up, it looks like the specular highlight is getting larger, but really all that's happening is it's getting brighter, and you can see it's a perfectly flat disk inside because all of these pixels are clipped at RGB 255, 255, 255. So the very center of this is much brighter than it's being displayed on the monitor. It's just that the monitor can't display it. It doesn't go that high. So don't mistake that specularity is the highlight size. It isn't. It's the highlight brightness. It's the intensity of the specular highlight. If you want to talk about size, we talk about glossiness. Glossiness is the size of the specular highlight. Now I want to talk about where specularity and glossiness come from. I'm describing specularity as the reflection of a light source. The question has to be raised, why not simply use reflection? And the answer is, and you can see when we turn reflection up, that we can see other objects in the scene starting to be reflected in this material. The problem is that light sources aren't visible objects in the scene. All they are is locations in space from which rays originate. And because they aren't actual geometric objects in the scene, there isn't any geometry to reflect, unless we actually built a geometry light and put it where the light is. And in most cases we don't do that. So we need a special way to reflect lights in our geometry, and that is a tool called specularity. Specularity and glossiness basically are the two tools. Now I want to talk about the real-world definition of specularity, because this is where it can get a little bit confusing. The CG term specularity came from the Phong shader. When the Phong shader was originally written, these were called specular highlights, and people took it to mean that a highlight from a light is specularity. However, in reality, specularity means the smoothness of a material. So a material can be incredibly smooth but not show a light highlight. For example, a piece of glass is extremely highly specular, but it's not very reflective. A piece of polished marble can be highly specular, but if there's no light turned on, there is no specular highlight, even though it's incredibly highly specular. Water is very highly specular. Anything that is really incredibly smooth, usually so smooth that you can see reflections in them, that's something that's highly specular. Now, I want you to chew on this for a moment. Think of a piece of glass. Most people, when they think of glass, they think that it's extremely reflective because they can see their image reflected in it. That's not true. Glass is not very reflective at all. Glass is maybe in that 10 to 15% reflective, and the other 85 to 90% of light just goes through it. How do you know that? Well, you can see through glass, and seeing is the process of receiving light. So if you can see beyond glass, you know that a lot of light is coming through that glass and into your eyes. Glass is highly specular. In other words, it's incredibly smooth, but it's not very reflective. It doesn't reflect much light. Most light transmits through it. So when we're talking about values of specularity and reflection and transparency, we have to be careful not to add them up so that they make like 300%. Like if I wanted to make this material look like glass, I would probably make it 90-ish. Let's just type in 90% transparent. That doesn't look much like a piece of glass, does it? It needs to be reflective. People say, well, glass is like 100% reflective. Well, what if I make that reflection 100%? That sort of looks like glass because you can see things reflected in it, but look at how bright it is. It just doesn't feel right. And this is because we're not obeying conservation of energy. We need to understand that the light, let's just check the intensity of the light. The light is on at 100%, which means that all of the light that's reflected off this material should end up being around 100%. Well, right now we have 100% diffuse plus 100% specular, right where the specular highlights are, plus 100% reflection. So we have 300% light where the specular highlight is, and everywhere else we have about 200% light. That's obviously way out of whack with reality. So what I'd like to suggest is if most of the light is either going through, so 90% of the light is going through, and then I'd say that 10% of the light is reflecting, and then I'd say that that's 100%, so I'd say 0% of it is diffuse. And that's starting to look an awful lot more like glass, except this specular highlight is a killer. The glossiness value is too low. So what glossiness means is the size of the specular highlight. And the smoother a material is, the smaller those highlights will be. So we want a very high glossiness. It's pretty intuitive. You think of something, if something's incredibly glossy, then it's really shiny like a marble. And if something's not very glossy, it's kind of plasticky. So you see how this is feeling kind of plasticky, and it'll feel even more plasticky as we turn the glossiness down. Do you see how that feels more like plastic now? But if we turn this way up till we have tiny little specular highlights, that starts to feel an awful lot more like real glass. So just to reiterate on specularity, glossiness, and reflection, because they're all kind of what we traditionally think of as reflection, even though color and diffuse are also reflected light. Specularity is the reflection of light sources in the scene, and reflection is the reflection of other geometry in the scene. And those two things are necessarily split up because we need different solutions in order to calculate these two things. So the single value of image reflection in a material has been split up into two methods called reflection and specularity, even though they're both reflection. One reflection value for objects and for geometry in the scene, and one method of reflection for light sources. And then glossiness deals with the size of the reflection for light sources. Now theoretically, if this glossiness is 100%, this specular highlight should be smaller than a pixel. It should actually be invisible, but NewTek has done some adjustments so that it won't go smaller than a certain size. And that's fine, because you usually don't need it much smaller than that. But you'll see as you turn glossiness down, the specular highlight becomes wider and wider, making it feel more plasticky. The reason why it feels more plasticky is because plastic materials are rougher than, like for example, a glass ball. So when the photons hit the plastic material, they're going to diffuse more. They're going to scatter and blur out more. And what this causes is scattered, blurred light reflections. That's exactly why this feels more plasticky when the glossiness is lower and the specular highlight is wider. So I can make this very easily feel like a plastic ball instead of a glass ball, simply by I can just turn off the reflection entirely. And now, although it's transparent, the surface of it feels incredibly plasticky. Also, if I turn up the diffuse value to take up that 10% of reflection, then that's definitely starting to feel like more of a plasticky ball than a reflective one. So specularity, glossiness, and reflection are all interlinked. Energy conservation needs to be applied when we're thinking about these things. But these values have been decoupled. And anytime values are decoupled, as they are with color and diffuse and specularity and reflection, which are all different ways of expressing reflection of light, whenever these values are decoupled from each other, We need to put them back together cautiously and understanding conservation of energy and doing our best to create a material that's close to correct and is valid within the scene. Alright, next let's take a look at transparency. Transparency, believe it or not, is another way of expressing light reflection. And now I know this is starting to sound like a theme here. Just about everything here has something to do with how light is reflected. And if you've perceived that already, good for you, because everything that you see is either emitted light or reflected light. And all of these values have something to do with either emitted light or reflected light. In the case of transparency, what we're saying is how much light is reflected and how much goes all the way through. So this is a form of absorption, but since it goes through the material, we have a different term for it. It's called light transmission. And light transmission is involved in transparency, in translucency, and in things like what we call subsurface scattering. And subsurface scattering is merely light entering a material and then exiting again somewhere else after it's been diffused or scattered around. In the case of transparency and CG transparency specifically in this channel, we're talking about the ability to see through something. So we mean, when we say transparency, we mean transparency without light scattering. So direct transparency. Something, we know that the word transparent means you can see through it, some amount. So as we turn up our transparency, what we're saying is more light goes directly through this material without changing direction, without scattering or anything. A transparency of 90% means that this material is reflecting 10% of the light that hits its surface. Alright, now, something else often happens to transparent materials, and that is that the light that enters it, instead of reflecting backwards, simply bends. And that is called refraction. The main difference between reflection and refraction is that with reflection, the light will bend more than 90 degrees, and with refraction, the light will bend less than 90 degrees. So they're both forms of simply bending light, but because one goes through the material and one bounces off the material and comes back towards us, we have different terminologies for those things, but the function is essentially the same. The only difference is how much the light bends. In a physical material, reflection and refraction would probably be the same value. Or you'd have the bending of light, and then you'd have a refractive index, which would tell you whether or not the light bent more or less than 90 degrees. In the case of our transparency here, we have a refraction index only for transparency, not for reflection. And we say the light bends a certain amount by the refraction index. If we say the refraction index is 1.0, we're saying that in light that passes from air into air, it won't bend at all. So the refraction index is the amount of bending that occurs at the material surface. And we know that glass and water have a refraction index of around 1.3. So if we set the refraction index to 1.3, we'll see light bending as it passes through this material, roughly the same as it would if it was water or glass. So let's just put 1.3 in there. So you can see some refraction happening. I'll turn smoothing on here so we don't get the faceting. So you can see the distorted, this ball here is distorted through this material now. And that's because the light is bending a certain amount. If I increase the refractive index, you'll see that the light bends more, and you can see the image change. You can see more and more of the surrounding geometry getting bent into that glass. I can also do negative refractive indexes. So negative 1.3 goes in the opposite direction. You would use a negative refractive index if, for example, your scene was underwater and this were an air bubble. What negative refraction index is? It makes the light bend in the opposite direction. So for example, if refractive index makes light bend 28 degrees to the left, if that's a positive refractive index does that. If you make that negative, the light will now bend 28 degrees to the right. So that's the purpose of refraction index. And what we have to understand is if the refractive index is 1, what we're saying is that the density inside this ball is the same as the density outside of the ball. And we're imagining that the density outside of the ball is air. It's in a room. It's somewhere humans experience. And air has a refractive index of 1.0. That's our constant. That's our standard by which everything else is measured. So if this were a material made of something of the same density as air, then you'd be able to see right through it just like this with no image distortion on the far side. But as soon as we start bending the light, what we're suggesting is that this material has greater density than the air outside of it. Or, if we do a negative refractive index, negative 1.5, then what we're saying is the material inside this ball has a lower density than the air that's outside of it. Or, again, you could say that what's outside of it is water and that it's air on the inside, in which case it would be a negative refractive index of roughly 1.3. Sorry, negative 1.3. So that's quite enough ranting about transparency and how light reacts in different densities and so forth. I think you probably get the idea. In most cases, you'll be probably doing glass, so you'll want a high transparency of probably like around 95, and you'll want a diffuse value filling up the other 5% of that. And you'll probably want a refractive index of around 1.3, which is the most commonly used refractive index, glass and or water. So those are probably the settings you're most likely to use. But if you want to be really accurate about the refractive index, for example, if you're doing something technical, a technical model or something, it's very easy to look up refractive indices on the internet and find lists of the refraction index for various different materials. You can just plug them in here. Myself, I usually start with something that I know is in the ballpark, and then I adjust it until it feels aesthetically correct. And that may, that's not physical, but my job is to make finished images that look great. And whether or not they are physically perfect is, in my job, usually a secondary consideration. Let's take a look next at the translucency channel. So translucency is also transmission of light. In the case of this particular parameter in light wave, what they're talking about is the transmission of light through a single thin polygon, not through depth like you might with subsurface scattering. Translucency is kind of the predecessor to subsurface scattering, but you'd use it for lampshades or a piece of paper that you want to see light transmitting through, or leaves, or something that's just very thin. Just a single polygon of thickness. So I just need to set up this scene. I want you to see how this scene is set up so you'll understand what's going on here. So what we're going to do is we're going to take all of these objects and rotate them so that the balls are behind the plane. And obviously I'm going to have to go to my surface editor to make my ground plane double-sided. There we go. And I'm going to take this light and shove it behind here and turn it around so that it's facing towards the balls. So what will happen is the balls will cast shadows onto the ground plane. Let's just take a look at that. I'm just going to the perspective view here. So there's the balls, and they're casting shadows onto the plane, onto the ground plane. If we look on the other side, we see nothing because there's no light on this side. So if I go to the surface editor and take my ground and turn up translucency, suddenly we start to see the shadows cast through the material as though it's paper thin, like a piece of paper or cloth. Now this in itself is not incredibly useful. And the reason it's not incredibly useful is you can see that these balls are different sizes and they're standing different distances away from this plane. However, all of the shadows are perfectly sharp, so they look really fake. Well, here's a great way to deal with that. If we open our light properties panel and change this light from a distant light to, for example, a spherical light, all of a sudden the shadows change, but what we want to do is change the size of our spherical light so that we can get a little bit of softness on those shadows. So I'm going to change the size of the light. Okay, now we're talking. So you can see that there's some really beautiful ray trace soft shadows happening. Let's look around the other side again. So you can see the shadows cast from the larger spherical light. We'll actually turn on the OpenGL overlay so we can see the size of the light source. Let's bring it down again. The size down a bit. So that's a much more realistic way to make use of translucency. And even if you need your shadows to be fairly sharp, all you have to do is size your light down and get them pretty sharp. Just don't make them completely sharp. See, this is getting to be fairly sharp, but you see that the ones that are more distant have these beautiful softnesses out at the edges. So these shadows, these cast shadows in this translucency, feel a lot more realistic. And in fact, if these were people standing away from a curtain like this, you can be sure that the cast shadows would be pretty soft unless they were pressed right up against the curtain. So that's a little overview on the use of translucency. And of course, once again, you can animate the translucency and you can apply texture maps, so you could put some kind of a pattern for translucency over here if you wished. Okay, and then last but not least, we have a bump map channel. This is not true displacement. Real displacements are handled in the deformation tab of object properties. And they are totally separate from the material shader. So let's take a look at how bump maps work. They're pretty straight ahead. Let's use our second ball over here. And once again, I'll turn smoothing on so we can take a look at it. So bump can be any value you wish it to be. Nothing is happening right now because there's nothing applied. In the case of bump, you must apply something through the texture map. So let's start with a simple image map. I'll do a spherical projection because it's a sphere. I'm going to pick an image that's sitting on my desktop. I have one here called stripes. And I'm going to wrap it around the y-axis. And there you have it. You can see the image has three raised areas, and that's defined by the white areas, and 1, 2, 3, 4 lower areas that are defined by the dark areas of the image. And that creates the illusion that there's some displacement happening on here. Now I don't have to use an image. I could, but I don't have to. I could instead add a procedural layer. And I'm not going to delete this. I'm just going to turn it off for the moment. And I'm going to add a procedural layer. And I'll just use this default turbulence, and you can see it makes the surface look kind of crumpled. It's just a shading trick. It makes the material appear as though it's bent in ways that some portions are pointing more directly towards the light and some are pointing away. But if you look closely at the silhouette of the ball, you'll see that it hasn't changed. Watch what happens when I turn off this layer. So the ball is actually not displacing. It's just a bump map. It's just fake. And we could put these together though too. They're both layers, so we can have both of them together. We can simply turn stripes back on. You don't see it yet because the top layer is 100% opaque. So let's just turn its opacity down to 50%. And now we have the two of them mixed. We can also turn the stripes down to 50%, so we can actually effectively manipulate the amplitude of the bump here as well. It's one place we can do it by its layer opacity. We can also do it here. There's another place we can deal with the texture amplitude of this layer. Or if we have them both in a place where we want them, we can deal with the amplitude right here, the bump percent. So the lower I turn it, the lower all the bump goes. And it can actually go into negatives as well. So bump is incredibly useful in places where you don't need to see the displaced silhouette of an object. And the reason it's incredibly useful is because you're not hit with the actually really heavy processing time that's required to do actual geometric displacements. They can be quite expensive. So typically what you'll do is you'll use a displacement map only for large visible changes in the silhouette, and anything smaller and inside that you'll use a bump map, or these days even more often you'll use a normal map. And here's where you add your vertex. Normal map here. The normal map has essentially replaced the use of the bump map in most cases. The difference is normal maps need to be generated through software, and bump maps can be hand painted. So you can just simply paint a black and white map, and where it's white the surface will be raised, when it's black it'll be lowered. So bump maps are still quite useful, but there are utilities out there that'll just help you switch bump maps into normal maps and so forth. So that covers it for the channels on the basic tab of the surface editor. Next we'll take a look at the advanced tab. Okay, looking at the advanced tab now. We'll just take a quick look through all of these parameters. Alpha channel. This defines how this material, the currently selected material, is going to behave in the alpha channel. So if the object is perfectly opaque and we want it to be visible in the alpha channel, so we can cut it out. For example, if we're doing multipass renders to be composited, we can just leave this at surface opacity. And I'll show you what it looks like. I'm just going to do a quick render. And first I'm going to turn off global illumination, just for speed of render. Okay, so there's our render. And if we look at the alpha channel, we can see that each one of these pieces of geometry is cut out, including this one, our second ball here. So they're cut out, they're part of the alpha channel. There are times when I might not want that to be part of the alpha channel. I may want it to hold out for something else. So I can change its alpha value. I can do it, here's one way I can do it. In the material editor, the surface editor here, I can change the transparency. So if I change the transparency to 50% and then render it, I'll see in the alpha channel that the alpha is 50% for that one material. Or I may want it to not be transparent at all, but still not be in the alpha channel. That's fairly straightforward. I can set it to a constant value, and now it'll be whatever value I set here numerically. So if I want it to be gone, I set it to 0. Now when I render it, it still appears in the render, but in the alpha channel, it's gone. It's actually cut out of the image. So those are ways to deal with how the alpha channel is going to appear in your render. And of course, you're only going to see that if you render a file format which is RGBA. Alright, I'll just set that back to default, 255, and set the alpha channel back to surface opacity. Those are the two ones I usually use the most, surface opacity and constant value. There's something down below here called special buffers. And what this is these are just 4 slots where you can put 4 different values. And they're just a value that you can apply to a material. And that value will be picked up by a plugin, some other process, to be used in rendering this. So we're not going to deal with special buffers in this video, but if you want to know about special buffers and ways to assign data to a material that isn't otherwise there, that can be used elsewhere, then look through the manuals. It explains special buffers fairly extensively. Glow intensity. This is a post process, so you can make a material glow by turning up the glow intensity, but you also have to enable glow in the image processing tab. So here's something called enable glow. We turn that on. We have to turn the intensity up. So I'll turn it up to 100% here too as well. So now it's 100 here, it's 100 for the material. So this is the global glow value. When I do an F9 render for this, you'll see that there's kind of a glow around it. and I can increase the radius. Let's make it 24 pixels, and I'll do another render. There you can see the glow around the material, and it's a pretty fake glow. It's a post-process glow. There are a lot better ways to do it. This effect could be achieved a lot more effectively and with a great deal more interest in compositing. However, you may be after something quick and dirty and simple. You may not require anything really fancy. So that's a way that you can add a glow to any material. It's on a material by material basis. I'll turn that off. Render outlines. This is a way of doing just a wireframe render of any material. So if I F9 that, you'll see that all is now a wireframe render. And that's pretty interesting. It also casts shadows for a wireframe. And I can thicken that wireframe. I can change the thickness of the wires right here with the line size. So I can go for a line size of maybe 4. Let's try that. So you can see I have quite a lot heavier lines now in my line render. That's a nice trick. Vertex color map. If you have painted the vertex colors, here's where you load a vertex color map. Color highlights. This is an interesting and well used one. Here's why. If I want to make, for example, brass or gold, first of all, I want my material to be pretty reflective. So I'm going to turn it up so it's quite reflective, and I'm going to want it to be not very diffuse. Now, gold is kind of amber colored, so let's see if we can find a nice ambery goldy color here. Something like that. But the diffuse is at 100% and the reflection is also nearly 100%. So we don't have a conservation of energy. We need to turn our diffuse down to like 7.5% to make the conservation work properly. Except that when we turn the diffuse value, because it's multiplying by the color disappears out of it. If I turn the diffuse value right to 0, then it loses its color completely. So the way to bring the color back in the advanced tab is by turning up color highlights. So now you get the color back in the reflection. This is where I had said earlier that I thought it would be useful to have RGB in reflection instead of just a single value, because using the color highlights in the advanced tab is kind of a hacky way of getting around the fact that we're reflecting all light equally. And the fact is that gold and brass and colored metals like that are reflective yet colored because they only reflect certain wavelengths of light and they absorb other ones. But our reflection parameter here only allows us to reflect all light wavelengths equally instead of allowing us to pick and choose between them. So I really think the reflection tab should have an option to reflect red, green, and blue separately. And in that case, we wouldn't require the color highlights in the advanced tab. But in the meantime, this works just fine. If you're trying to make a colored metal, then you'll lose the color by dropping your diffuse, and you need to bring it back using color highlights. Okay, so the next parameter here is called color filter, and what color filter means is if the material is transparent and light is shining through it, that the light will filter through that and pick up its color. And let me show you exactly what it means. So say we have a kind of a green, let's do like a dark green glass or something. And we'll turn the reflection down to like 10% because we're going to make some nice glass. Transparency, we'll say, is 90%. And we want to bring our color highlights back up. And you can see, if you look carefully, you can see the shadow from this ball, which is supposed to be green glass, is gray. And green, if it's green glass, of course, it should be casting green light. And the way to do that is to simply go over here and turn up color filter. Oops, I went way beyond 100%. And when you turn up color filter, the glass now casts the correct color of light. So that's working an awful lot better. So that's what color filter is for. Additive transparency, if you have multiple items that are transparent in front of each other, it'll add the transparency together. And diffuse sharpness, here let me just get back out of this and make this not transparent. Okay, so diffuse sharpness is about sharpening up this shadow terminator. So where you have shadow going around a ball or an organic shape, there's going to be a kind of a gradual fall off. Now, some people feel that in the case of much larger items like planets, that fall off is much sharper. I personally disagree with that. However, this diffuse sharpness tool here is for those people who do believe that or have other reasons to want the shadow to be much sharper. For example, it could be useful if you're doing a toon shaded sort of thing. So if we turn our diffuse sharpness up, you can see how that shadow terminator sharpens right up. There's another mysterious parameter down here that I'm actually not familiar with called bump drop off. I've tried it out. I don't really know what it does, and I couldn't find any reference to it in the manual material either. So below that is a compatibility drop down, and that's if you have materials made with older versions of Lightwave and you want to use them in this current one, you can change your compatibility for the materials. And that covers it for the Advanced tab. Alright, let's take a look into the Environment tab now. The Environment tab is about what is around the material. So in many cases we have a CG environment where we have objects in the foreground and we just have this empty black background. And in the case where we're reflecting and refracting, we need a lot of things to reflect and refract into the material. Sometimes we don't want to go to the trouble of creating all that geometry, so we can just use an image in the reflection options and the refraction options. And I'll show you what I mean. If I turn up the reflection of this ball material, the second ball here, I turn the reflection up, and you can see, especially if I turn diffuse down, you can see other things reflected in it. See, you can see those reflections. Now, if I open up the object properties for these other balls here and just make them unseen by camera, I'm just going to make them disappear. And I also have to make them unseen by rays so they won't be seen in the reflection. Now, if I go to this material, and even if I make it reflective, you don't see any difference because there is nothing for it to reflect. And sometimes we're creating materials in a situation where there is nothing for them to reflect and we wish there was. The easy way to put something into reflect is to use this spherical map parameter. So instead of the reflections, by default we'll ray trace reflections and they'll use whatever's in the backdrop. But sometimes we don't want something in the backdrop. We want to render black because we're doing render passes or whatever, and we don't want ray tracing, so we use a spherical map. Now I'm going to pick a map that I just found on the internet. I'll show you what this map looks like. It's just, in the image editor here, it's just a panoramic image. I'm not going to include this with the content because it belongs to somebody, so if you want to search for an image, just search for one on the internet. When I put this image into the reflection map, you can see that it's now reflected in the material. You can also do reflection, you can also do spherical map and ray tracing if you wish. So if I go back to my object and I turn it back on, then you can see they're reflected, and also so is the spherical map. It's like having a background map without having to put it in the background. That's basically the intention. Now there's a control here called image seam angle, because this image is, because it's just a panoramic image, it's going to have a seam in it somewhere, and if the seam appears right in your image where you don't want it, you can turn the image so the seam appears somewhere else. Do you see how the image is rotating? So you can place this seam behind the camera or whatever if you don't find it in a convenient place. Now I just want to turn down diffuse so we can take a good look at this reflection. I'm going to turn my reflection value up so we can have a nice bright view of this image, because I'd like you to see what happens next. Okay, so there's our reflection happening. In environment, we have this thing called reflection blurring. And if I turn that up, what you're going to see is that the reflection softens as though this isn't a polished ball bearing anymore, as if it's a little bit roughed up, as if it's maybe brushed or something. And that's what reflection blurring is. It's just roughing up the surface. It's mocking as if you were roughing up the surface a little bit. If reflection blurring is at 0, then we're saying that the material is polished to a very, very smooth shine. It's highly specular. And as we turn the reflection blurring up, we're saying it's less specular. And therefore the light is diffusing and making the image go blurry. And if we do an incredibly high reflection blur, what you'll see is that the image information actually starts to disappear as though this were just a dull metal ball. And you see you can go so high, you can actually probably go so high that the image completely disperses. This is why you don't see an image on a piece of paper. It's not because the piece of paper isn't reflecting light. It is. It's just because the light itself is being diffused so much that the image information becomes diffused, becomes scattered and blurred like this. So reflection blurring can be used to simulate metal that isn't quite exactly shiny. However, this reflection blurring is usually fairly slow compared to the blurring work that you can do inside the node editor. So that's probably a recommended path if you're going to do some reflection blurring. Reflection samples will improve the quality of the reflection blurring if it's too noisy in your render. And then here, let me just turn that off to backdrop only. And then same thing again for refraction options. So let's make our material refractive. We'll turn this reflection off, give it some nice high transparency, turn the reflection options to ray tracing, and we'll do ray tracing and backdrop. And backdrop is black, so that essentially makes it ray tracing only. And now we're going to, here I'll just remove that image, we're going to put an image into the refraction map. So put that same image in there. And we'll switch the refraction options to spherical map, or maybe ray tracing and spherical map. And we won't see it quite here yet. The Viper is not supporting that yet, so we'll just do an F9 render. And if you look carefully, you can see that that image is around the edge of the refraction. I'm actually going to turn off the ray tracing so we can see just the spherical map by itself in the render. And now you'll see that the image is being refracted through the glass ball. So you can have backgrounds to be refracted through the glass ball without actually having to have geometry in the background, without having to have a backdrop image in, simply by using the refraction map here. The image seam angle is the same idea. You can rotate it. You can blur the refraction. So if I set this to 50%, for example, you'll see that the refraction is quite blurred now. And in fact, you actually don't need an image in to blur the refraction. You don't have to use the image at all. Let's just set that to none, set this back to ray tracing and backdrop, and set our refraction blurring back to 0. And you see that we have a nice refraction going on. And as we turn up our refraction blurring, you can see how the image blurs through there until this starts to feel like frosted glass. Now here's a nice way to make some frosted glass. We can make, let's make this a red frosted glass ball, like the kind you might see hanging out on a Christmas tree. And we have our color highlights, our color filter turning up, so it's casting nice red light and everything. So that's how you might go about doing that. And we might want to turn on, if it's a glass ball, we'll turn up a little bit of reflection. But guess what? We're going to go back to our environment tab and turn up, oh, reflection blurring is already up. So now we have blurred reflections and blurred refractions, and we're casting the right color. So it feels kind of like a glass ball. But we'll get more depth into some more complex glass later on in this tutorial. The last tab we're going to look at is shaders. We'll look at that next. Okay, the last thing to take a peek at before we get into starting to create some of the more common materials is the shaders tab. We're not going to spend a lot of time here. There's a lot of shaders in here. They're well documented in the manual. We'll probably be looking at Fast for now. There's not a lot more in here that I use regularly. So it's really up to you to go ahead and try these out. They're basically effects that you put on top of your surface, and we will look at one or maybe two of them, and the rest, as I said, are very well documented, so you can go through them and figure out what they do. Of the other ones, the most interesting ones are probably the thin film one and maybe the interference one I have used before. Most of these other ones, I used to use the surface baking one, but now we have a surface baking camera that's much better. But they're all useful. I work in visual effects, so I don't find a lot of use for most of these. However, Lightwave is used in so many different applications for so many different things. These are all valuable somewhere, or obviously they wouldn't be in here. So that's it for the shader tab.